is I guess a walkthrough of the process of finding different kernels that are memory bounded in terms of the throughput, and identifying how we can change the data types that are used in the kernel to to pack more I guess floats inside of a single read from memory to be able to optimize the speed of how much the kernel can process. So yeah, I'll just get started. So there's another video tutorial on how to get this set up that I just posted to YouTube that you can follow. But yeah, once you have it all set up, I'm just going to go straight to the terminal and go to oops. Straight to the repository. So I'm going to actually start with a fresh git clone of the repository just to kind of start this from scratch. Oh, all right. So in this repository, we have all of the Cuda kernels in their own work, in their own kind of working file. And it was posted earlier, all of in the kind of state of the union for this project, all of the slowest kernels relative to what's being optimized by something called Cutlass. And so taking a look at that gives some ideas on which ones would be good to take a look into. And so for the first one today, we'll be taking a look at this, I believe it's called GELU forward. So if you take a look at that file, it just has instructions on how to run it. So to start off, it'll be yeah, just running this to compile it. And I'm going to have this open in Visual Studio Code. I'll just reopen a new folder where, oops. All right, yeah, in a new window. There we go. And so yeah, I'll have this is what we're looking at. And yeah, let's go and run it. Actually, I think I might be able to open it directly here. Oh, that'll make it a lot easier to see. Let me make this bigger so that it's easier to see on video. But to compile it, yeah, we're using that previous command. That's the command that's included in there, but to be able to do, to look at it in the profiler, I like to use the generate line info command as well. So let's just go back to here and, oh. I already have the command saved. All right, so that's how we compile it. Nope. What am I doing? Oops. Almost there. So I just need to put that parameter before I specify the file input. So I go generate line info. Oh, I'm not in the Cuda. That's what it was. Okay, so yeah, now that it's compiled and it has all of the profile information, you can run it by just doing GELU forward, and you can take a look at how many kernels there are available to work with. So in this case, there's case 1. So there's only one of them, so I'll just run the first one. And it runs all the benchmarks. And one thing to note is when you're looking at the benchmarks, when they're at the milliseconds that are low enough to where they're in the 0.00, or in around the hundreds of nanoseconds, it's a lot harder to visualize the impact that it'll have on the actual training algorithm. And the best way to verify this first is to, when you're looking at the kernel types that we're being told to be optimized, you can see how long in milliseconds that each one of them took. And so in this case, it actually took 3.5 seconds. And so what we need to do is change the profile in a way that will allow it to kind of replicate that. So to start off, I'm just going to multiply the amount of input to be larger so that we'll get a better understanding of like how it runs. So maybe times 8, or let's do 16. And compile that again, and then it'll run at like a higher speed. I mean, it'll take longer to run, so you get the better indication of like what it would be like in the actual like algorithm. All right. So now that we have a good profile for that, the next step is to run it in the profiler. And this is the command that I would use. I'll post all the links there as well. When you run this, all you need to do is just pass the command that you were running previously into here. So in this case, it's GELU forward. And we're running the first kernel. Oh, whoops. And it does take a bit of time to run. And actually, you know what, let's stop this for now. I missed one step. It runs for 1,000 times, but that'll take way too long to run the profiler on that. So you actually have to recompile it and run the profiler on a smaller number of repeat times. And yeah, I did a video on just explaining how to get this set up, but yeah, I'd watch that intro video if you haven't gotten this set up first. But the workflow that I follow is I will, after running the profiler, I'll just like SCP it to my desktop. I'll call it profile 21. Oh, it looks like it's profiling per block size. If you wanted to speed it up and you knew that you were only going to profile it for a specific block size, what you can do is just remove the block sizes here, and it'll be faster. All right, so it is now profiled. Where did I save this? Oh, in my home folder. Okay. Oh, whoops. File, open file. There we go. And so because we did the show lines, we're able to actually see like on a line-by-line comparison of where all of the weights are. And you can either go to the details page and you take a look at what's the memory throughput or the compute throughput, or you can go to in the code, take a look at in the source where all of like the warning signs are, where all the warp stalls are, because that's where it's getting delayed the most. And you can see that the errors that are popping up are on this like lerp command. Oh no, wait, this is not the right profile. I am sorry. Whoops. I knew that kernel is not looking right. I'm looking at a different file. All right, let's try that again. There we go. Go to one of the later ones. So yeah, you can go into the details and you can see that there's a lot more memory throughput than compute throughput. And then when you go to the source here, you can see that all of the weights are on this one right here. So at 54% of all the warp stalls are on this line for doing the kernel. And you have the warning sign that this line is responsible for a number of warp stalls. And if you look at the type of warp stall that it is, it's type long scoreboard. And what I did is I just went into ChatGPT and asked, like, what does it mean when it says like long scoreboard? And it essentially means that it's waiting for values to get back from the memory. And so if you look at which one is what memory it's being waiting on, you just see like right in the assembly before it, load from global. So it's taking a while to load this like float xi. So here we can recognize, all right, so this kernel's memory input, a memory like bounded, and the value that it's trying to get is this, and it's not really bounded on passing the value back or in doing the actual like calculations. Because if it was in the actual calculations, like you'd see a different type of like warp stalling. So the next step would be to this is where I got help from others on the Discord that mentioned that you can do something called, or just be able to concatenate a bunch of floats together and then read it all at once using something called a float 4. And so that's what I'll be doing now. So looking at this kernel, I'll first start by just copying the kernel and making GELU kernel 2. And I'll just say optimization with float 4. And then we go into here and you make a second case break. And we make a second kernel launcher. I'll call it forward 2. And GELU kernel 2. And we'll just double check that that worked and that we can run it. Sweet, so now it's running out of that new kernel. And to take an example of what it looks like, the float 4 value, let me just find another example in one of the other kernels that has it to just show like what the end state should kind of look like. So you have a float 4 value that you're reading, and then you index that float 4 at each of its intervals by looping like by 4 through everything, and then getting the value at like one of the 4. So it's essentially just like you are getting 4 at a time and then iterating on 4 at a time. And this helps because you're able to make 4 reads from memory like at one point and then batch all of your calculations together, so that in theory you're not just always waiting on the memory request, and that all of your memory requests are happening in parallel. So going back to here, one thing to start off with is we're going to copy that function that allows you to index the float 4. Let me just get that. So vecat, just going to copy that into here. And then we will go into what I'd really recommend is, I'm just going to copy this into ChatGPT. All right, I say so I have this Cuda kernel, and I want to optimize it by using float 4 instead of float, and iterate through them using the helper function. And I'll just like copy over that vecat helper function. So yeah, especially when you know what you're looking for, it makes it so much faster to kind of code through this approach. So we save the value that we're receiving, you receive the result, and then you just iterate through all the values. So let's kind of copy that one. All right. Yeah, it seems right. So float 4, input n, you get your IDX, and each thread is going to handle 4 floats. And following the same thing, that as long as it's less than n. Yep, looks all good to me. The only other things that need to happen now that I'll delete this, because we have it right above, is that while we're passing in the values into this function, we need to cast them to float4 type. So float4 pointer. Just because we're now treating them as the inputs as float4. Let me just double check that there's nothing else that's funky that's going on here. So yeah, this will speed up because it's not doing a write to kind of global memory, and then all of the global memory writes are going to happen together. And let's try it out. Oh, first I have to compile it. And these are the times where we're looking at this before to compare them to. That doesn't seem right. So it's actually a little bit slower there. Oh, okay. So then now that you've done that too, then you just, the only other thing is you need to decrease the grid size by 4. Because you, because since you're operating at 4 at a time, you only need to look at 4 at a time. I mean, you need to only look at 1/4 of all of the block sizes. I think that's the case. Let me just divide this by 4 and see how it goes. Interesting.
You have forgotten to recompile.
Oh, yep. Good catch, good catch. And I was so confused because I know it works because I've done it before. I guess that's lucky that it worked for me the first time. Yeah, okay, check a look at that. So the speed up isn't that big here, but I think the trick is when I was first looking at this, I was trying to make it so that the milliseconds for the block size match what was in the actual like kernel. So if I was to like increase this by another factor of like, all right, let's say instead of 16, it was like 64. And then we want to run 1 compared to 2. It'll give a better indication of what the actual like performance improvement is going to be like. So glad I remembered that whole block reduction thing. Now, to clean this up, I'd imagine it's be a lot easier to optimize some of these if checks. But okay, so this one's a bit better of a comparison where recompiled with that higher size at 1, it'll take 2.3, and then if you were to do it in 2, would be 1.8. So yeah, definitely a speed up there by using that whole like float system. All right, so yeah, what else can we do to increase the speed of this? I think for now that should be good. Maybe I would include this all in one line. Don't need that additional float in there. And then instead of just calling that, I'll just call it the GELU. then I think just for the sake of making it smaller, we'll put these in parentheses and then multiply it by 4. We'll state each thread handling is free floats. And it might be better to just include this in the I think this bound check isn't required because the values that we're working with should be, that'd be a good check to see whether these bound checks are required. Oh, whoops. Missing something here. Oh, whoops. Yeah, an additional extra. All right. That should be the finalized version. I guess that only took a few minutes or so. Oh, okay, so we do need those checks. All right, I guess we'll keep that in there then. All right. Let's keep that as that. I is undefined. Oh, oops. Oh, shoot. I wasn't paying attention earlier that we do need that IDX at the beginning easier. Well, too much premature optimization. Let's go back to what ChatGPT said. Okay, it was IDX, and then this was I. Okay. All right, don't mess with what it provides. Okay. Just one last compilation. I'll put some comments in here just saying, better comparison to all right, I think we are done. So I guess the next step would be to update this into the actual train.gpt. So if we were to look at the GELU forward, there's the kernel, and it's using float x. So we might only be able to update this one now. There we go. So I'm just going to copy and paste the new GELU kernel. And then the next step would be to just finish the conversion of the float. Oh, and then dividing the block factor. Oh yeah, GELU forward kernel. What is going on here? Okay. Oh yeah, these have to be converted to float for a pointer. And we can confirm this by going back to train.gpt. There should be a command at the top to run it. Actually, I guess profile would be the one to check out to be able to run it.
Profile doesn't actually give you like realistic times for the entire model, though, because it benchmarks each kernel separately, and I think clears L2 caches between, so that might be slightly different from actually running the model.
Oh, in the profile, like in the kernel, like the development file.
So the profile script, like the profile.py file.
Yep.
At least that calls NCU, like the script you just selected, that calls NCU, which runs each kernel, I think, like 40 times and does all the profiling, which is really nice if you want to look at all the kernels individually. But I think it can give you misleading results if you want to look at the end-to-end performance of the model.
Oh, okay. Yeah, no, I'm trying to find the end-to-end performance just to compare like what the time changes are. I thought I just needed to compile like train GPT2.cu, and I think I just need to run that command, which is like nvcc. Kind of looks like this, and then I just replace this with train GPT2.
I think there is something in the make file that you don't even have to do the command yourself.
Oh, amazing. Okay. Oh, how do you make the F32 one?
You can run make train underscore GPT2 underscore FP32. No, so without dashes. Just train underscore GPT2.
Oh,
and maybe you want the full precision one. Yeah, yep, like this. No cool. No cool.
Oh, just like that. Okay.
So if you look into the make file, you can see if you scroll down all the way.
Oh, yep, all the way.
Yeah.
Yeah, these are the different things that you can generate.
Perfect. Okay, and then I still need to download all of the files. Shoot. Just new environment. This will be. I'm pretty sure I installed all the requirements already, but nope. Okay. Oh, I just pip. Okay, I guess I can do that easier. Let me. You know what? For the sake of just kind of going through development, I don't know how late everyone on the call joined, but I'm just doing an end-to-end of the improvement of this kernel, just as an example to use float 4 instead of like just using floats, to just show like end-to-end how to use the profiler to like identify it and then kind of build it, and using ChatGPT too. Yeah, I'm just at the step now where we confirm the times were different for the kernel, and then it's just seeing how much of an impact that made on the like final end-to-end training. And
the impact on final end-to-end is always a bit disappointing because like 80% of the time is just too bless. So
yeah. Well, what I'm hoping is looking at that State of the Union thing. It said that it uses approximately 3 seconds to in this function, and it appears that we've kind of optimized it by around 40%. So hopefully it'll reduce it by like 1.5 seconds, which would still like be pretty awesome for, because I'm pretty sure we can do it for this kernel, and then also for a kernel that doesn't even have its own training file. Like I think the next video I'll make is how to even make one of these Cuda training files, and then if we look at, I think it's Cuda backward. I mean GELU backwards. Yeah. So this one we don't even have one of these for. So I'm just gonna make one of those and then show with the float 4. I wonder the next step, now that people are working on train GPT-2 with the smaller like float size, the same principle applies, and I think it'll even have a bigger impact because you can fit even more floats into like that single read operation for the ones that are memory constrained.
I'm not sure. So my experiments at least were that first you don't have a half-4 or BF64 type, so you have to define one yourself.
Oh, yeah,
and if I remember correctly, if you do it with like 4 halves, you actually get the speed up, like get a different load operation. But if you do 8, which should be the same size as 4 floats, it actually does like 2 of the 4 half things.
Oh, rough. I wonder what it would be good.
By the way, since I joined late, like how much do you want this to be a presentation of you, and how much do you want to be a discussion here?
Oh, anything really. I'm just recording it so that I've done this for the last few days, and that it's been the main feedback is just recording it so that people can kind of listen through and learn from what we've been chatting about.
Okay, I just saw like the thing in the Discord always like for several hours going, but
yep.
We'll check what's going on.
Yeah, so I think I'm kind of done with this one. And then I guess the next one I'd be working on was that GELU backwards, but I was, in terms of your thoughts on, like, let's say for this one, how do you even want to set up the development environment for working with like 16-bit floats, or like, because these ones are all using the like other floats. Should we make like a second one? Oh, yep.
I mean, I'm not sure how the design is supposed to end up, but you might need to make some changes to how you compile stuff, because I think by default, the compiler has compatibility up to, what's it, like Pascal GPUs or something, which don't actually have BF16, so it will just spit out a big load of errors if you try to use them and don't say like the GPUs I want to use are recent enough. At least for me, the current trend file doesn't even compile because there are some errors, and I think that's like you need to have them recent enough Cuda and set correct flags. So that's going to be interesting.
Yep. Okay.
Yeah, I think this is what actually happened when you tried to run the makefile, right? Can you please try it once again? Just run makefile without.
Oh, yep.
Like what was the error? Can you expand?
Oh, yep.
Yeah. Those are the errors, like undefined functions, because it doesn't really know about these types.
For floaters.
It's the same that I'm getting. So.
Okay. So.
Yeah. Okay. And so I think what we need to do is to fix the makefile. Yeah, we need to let me file a bug and to tell Andrei that it is not compiling.
I think he knows. Like, he also posted some of these error messages. So.
He knows.
Yeah, sure. No. An actual bug is better than having some message in Discord that gets lost in the stream.
Okay. Good point.
I guess now that we have this, I can just run it. Let me see. I'll download the files and then. Interesting. Failed to open file GPT-2 bin. I think I'm just missing one instruction of like downloading the.
Have you? Sorry, I didn't quite see what was happening on the screen. Have you set this export tensors or write tensors or something when you ran the Python script? No, I think that was missing. Like.
Oh, I think
if you do
you have to run this first.
Train GPT-2, there is a like -- write tensors or something. Option that.
Oh,
so this doesn't actually generate this file. Oh, write tensors equals 1. I think I think you need to have 1 there.
Last time I just like ran it and then it starts off the program by just like downloading all the. Oh, okay. Yep. Just wrote all of the waits. There we go. So now it should be able to run. Oh, wait a second. That's faster than. No way. Wasn't it at like 73 or something like that? I swear we were having like a lot. There's no way that our improvement is that fast. I mean, that'd be amazing if it is. Yeah, he said yesterday that it was 76 milliseconds per iteration, and for me, I'm getting, I guess, 65. And then we can kind of compare it to what happened before. Yeah, still.
Usually, it's best to do a fresh comparison simply because some things, maybe your GPU was colder last time or whatever.
Yeah. Okay, so let me.
Especially with these small changes, right? Like if you're expecting only a change of 1 or 2%, then some weird things could make a difference.
Oh. Wow, that's kind of nothing. Actually, it's around 1 second, I think. Oh, 65.8. 66.2. Okay, 0.4 seconds. I'll take it. Okay, so now I think the only thing is just
Yeah, I think the times where you can make like really big impact are over because it's already so fast, right?
Yeah. No, definitely agree. Okay. Yeah, I guess how about just kind of continuing on and working on the if people would be interested in doing the backwards one intent. Let's like make a new file.
So the question is, do we actually need the backwards one, right? Because I think the only, like normally what you would do is the nonlinearity after the matrix multiplication really should be part of the matrix multiplication kernel, so they don't actually even load the data again, but before writing it out, you just write the correct like transformed result. But I think in the forward pass we can't do that because we need the information before the GELU also for the backward pass.
Yep.
But in the backward pass, I think we don't need to store like what happened before. So in principle, it should be possible to fuse that into the matrix multiplication. But I don't know enough about QBLAST to know if that's possible or not.
Oh, okay. Yeah, I mean maybe. It seems like one of those things too where that this same approach will like work as well. So I'm just hoping I can just do the same thing for now and just get that additional like let's say half a second.
Yeah, sure. I mean, as an exercise, it's definitely something that makes sense.
Sweet. So I'm maybe just going to start off by just copying the whole thing in here and then taking the kernel. All right. And let's go initial implementation. Then take the kernel that calls it. All right. Got a lot more input parameters. Oh, whoops. I wish I could just get ChatGPT to do this part. Okay, so it'll look kind of like this. So oh boy. Okay, so that go into there. And D out will be okay. I'll figure this out soon. I'm just gonna pretend that these are correct and then just work into the oh, we don't have a GELU CPU forward. Let me copy that over. GELU. Okay. Looks like we also have to copy those pragma things. Oh, and then backwards CPU. Output, input. Okay, input, output, and N. So to be honest, I'm not entirely sure how to make. Okay. Oh, these should tell us the size. This might actually take quite a bit of time to figure this all out. So this would be the D-imp. For people on the call that are kind of following, does this make sense? Like, can I just do this? Like just BT times C and for all of them? I don't know what all the values are supposed to represent, so.
So if you want realistic sizes, I think it should be like 4C instead of C, because the GELU happens in the MLP branch, right, where the network is 4 times wider, or you just multiply the initial value of C by 4.
Oh, okay, yep.
Just to have kind of realistic profiling. I think that's cleaner than having all the 4 times C somewhere, but yeah.
Oh, okay, yep. That, and then backwards. Oh, here we go.
Oh, repeat times 2 is probably also too low to get good estimates of timing. Like.
Yeah, I just actually, as a note, I do, whenever I do the profiling, I actually reduce it just like locally, because otherwise it'll just take way too long. Okay, I think that's definitely not going to compile, but worth a shot to just see what all the bugs are. Okay.
Yeah, but part of the reason why I wrote this profile like as a separate script is actually because it runs every layer just once instead of 12 times, so it's much faster to get a full profile of the entire model, and you just multiply all the repeated layers by 12, so it's kind of an estimate.
Oh yeah, no, thank you so much for making this. Like, this has been like probably the big difference in being able to like actually like get involved in trying out things. Like, if this wasn't here, like there'd be no way.
Yeah, like one thing that's extremely important in my experience is just being able to quickly check whether what you're doing actually makes sense. And so both unit tests and some sort of like automatic profiling make it so much simpler and more fun also to develop.
Yeah.
Because you kind of know that you get correct code and you can see how it gets faster, hopefully.
Yeah. Oh, it is not. It's
in the main script, because
Yep.
Android doesn't like C++ so much. There's a macro,
Yep,
but
yep.
for the development scripts, there's actually a function, and that isn't using like all capital letters. It's like just like CLDIF in lowercase.
Oh, okay.
That,
Like, oh, in the common, there's just a CLDIV that I can use.
yeah, that exists. Like you don't have to define it. You just have to. Yeah.
Oh, here we go. Okay, and then there's that. Oh, GELU scaling factor. Then D out is undefined. Const float is incompatible with type float. But I swear I just... Oh, on line 37. Oh, I just got to do this higher. No way. Maybe just like runs quicker. Oh, okay, illegal memory already. Block size.
So what I usually do if I get this is I run this in Cuda GDB and look at, like, it doesn't tell you if you don't compile with debug information, you don't know exactly where the error happens, but it prints you the line information and it prints you which thread, and then you can add prints for the specific thread that failed in Cuda GGB in the actual kernel.
Oh, I think Cuda GDB just broke the terminal bit. Oh. Oh, oops. All right. To run that command, you just do...
GELU backwards, I guess.
When you... Oh, GDB Cuda, yep.
The backward pass. No, this was like correct. It's that you was like you're selecting the forward pass, we're running the backward pass now. And I think the one doesn't work. Like,
oh, okay.
Can press enter now. Just press enter. But it's fine. It's still going to.
Oh, just like that?
Yep. Press enter. Again, enter. Enter until all this. And now we can type run space 1, and then it runs the program with the argument 1. If you press enter, does it print any more information? Yeah, so you know that something went wrong in this line with, oh, the first number seems completely off, right? Like that's, or maybe not. Like if you
I guess grid size would be n divided by, and n is,
Yeah, maybe the blocks are quite small and it's like everything flattened out. It's a one-dimensional grid, so that might actually be realistic.
Oh, okay. And then cube, this was, okay, and then,
but it fails relatively late. Like it failed in block 50,214. So,
oh, this probably, instead of adding a 4 here, I did it at the beginning.
yeah, that might be, yeah.
Oh, but I'll need to recompile. Okay, quit.
Yeah, that's.
Okay, and then, oh, that might have been it.
But I think this is somewhat helpful to figure out where these illegal memory accesses come from, because otherwise they're really hard to debug.
Yes, awesome. Okay, so now it ran. I mean, I don't know whether like it's actually working or not, but let's multiply this by 4 just to make it bigger, and then this by 64 to make it match before, so we get the similar time constraints. Oh, whoops.
If
Wait,
we're going
why
to
would you
recompile,
multiply the time by 64.
just to get more values.
Or just to make the, oh yeah, just to make the time longer so that when we do the optimization, it like, well, because in the State of the Union thing, it was approximately 3.5 seconds, right? So I was just hoping to get something that matches the 3.5 milliseconds.
The 3.5 is summed up over all 12 layers, so that's like 12 times the time of a single kernel.
Oh, okay, so it doesn't need to be that much. Okay.
But it still makes sense to get like a larger number of elements to, I don't know.
Yeah, I think this
Is
might
it?
be too big because the CPU version's just not running at all. How about I just...
Yeah, I think it's better to just increase the number of repeats if you're not sure about. Like this is currently the size that the default size that's running on, right? Like that's the realistic size, 1024, and this 4 times 768.
Oh, yep. Okay.
So if you want to have comparable numbers, you might just like.
Oh, perfect.
First, it's
there we go.
not
Yeah, I multiplied it by 4 and then it all kind of went together.
like in the print, just multiply it by 12 for now. Then it should have like comparable numbers to what the other script outputs.
Yep. Oh, is there multiplied by 12? You're saying this one?
No, not the, like if you just scroll down to the printing where we actually print out the timing information.
Oh, yep. And then that'll be comparable to, okay, so I'll just save these values
And
for
then,
now in like in a notepad, and then yeah, let's do
Yeah,
a second round of I'll show how I did it before, where you just go to ChatGPT and you say, I have another kernel that I want to use at what's it called? Oh, that guy.
I have a question for NGC92. Can I know what you're working on professionally, like at a real job?
I'm a PhD student.
Oh, okay. What are you studying?
Computer science. So I'm doing machine learning as my PhD.
Okay. Do you have any papers to read? Because I honestly, like, the question is probably like, how did you get into this field?
Do we now specifically the kind of Cuda programming or
Cuda programming?
General? So I think I've sent the link also somewhere in this channel, but we have a really good course at our university that I took like a few years back, which essentially has this exact workflow where you submit your code, then it gets sent somewhere, they run unit tests, they run benchmarks, and you get like immediate feedback whether you improved your Cuda kernels or not. And that's kind of where I started learning that. At the time, I think I learned more about like fast CPU programming because it's like a combined course. But yeah, over time, I extended it to
do you find it useful for your research?
Yes, but it really depends on what you're doing, right? Like, so one paper that we have is the kind of problems I'm working on are classification problems with very large output spaces. So if you have like 1 million labels or something, and then the last matrix in your network gets really, really huge. And the idea was like maybe people do this during inference, that you replace the dense matrices with sparse matrices, but if you have this huge matrix that makes you run out of memory during training already, maybe you could have a sparse matrix there already during training. And the original like implementations you got from TensorFlow and PyTorch for sparse matrices, they're kind of like terrible. So there was a natural task of implementing that a bit more efficiently.
Okay.
So I got the output. It's only a 30% speed up.
Still nice.
I mean, only that sounds like, I mean, that's basically great, right? Like, it's an extremely simple kernel with not many opportunities to make it faster, so 30% is actually quite nice.
Awesome.
I would say.
Sweet. Okay, so I guess I'll just copy this over now back to the original one, and then yeah, I think ready to make the 2 CRs or like pull requests.
Yep.
The problem is a little bit more
yes.
code.
I'd like to. I'm asking because at work, I work with researchers, and none of them kind of know CUDA programming at all.
Yeah, that's often the case, I think. So it's really difficult locally to find someone if you want to actually discuss like any in-depth details about what you're currently programming. Like, if you do some Python programming, there will be enough people that you can kind of brainstorm with. But if you want to do Cuda, I think that's one of the challenging problems.
Absolutely, yeah.
All right.
So a disadvantage of this that I see is that it would not work on batch sizes that are not divisible by 4. Or like
Really?
a combination of batch size plus sequence length.
Yeah, the batch size times sequence length, but I think that's a terrible idea anyway. Like all the fast matrix
Not having
multiplication.
it divided by 4, yeah.
Yeah,
I
like
agree.
all the matrix multiplication algorithms, they really also like nicer numbers.
Yeah. I guess this is where we can win against PyTorch, is that it is a lot more. We don't have to think about cases, these kind of edge cases where someone can just randomly provide you a weird matrix that is not divisible by 4.
Yeah, but I think also in PyTorch what happens is somewhat that at the beginning of the kernel there's one check, and then depending on where it goes, you do one code path or the other. So what you get is this whatever 1 gigabyte of download with all possible combinations. But in terms of speed, I'm not sure if it changes that much if you have good shapes.
Well, I wanted to go to bed earlier today, but here I am at 1 a.m. once again. I really like hanging out with you.
Well, same. It's so much more fun than doing my day job.
Oh yes.
All right.
I hope like hanging out on stream with more people as well. I'm in Europe, so I guess not as many people are in Europe interested in this.
For me, it's already 2 a.m. So.
Okay.
Wait, where are you based?
Maybe we can. Where are you based?
Finland.
Oh wow.
Okay. I'm in Germany.
Yeah, I'm originally from Germany, so.
Okay. But I don't speak German, unfortunately. German is very hard. Learning it at the moment.
Yeah, my Finnish also is very, very basic, so.
I think. Oh, let me revert this. And then, okay, add the forward one.
Can I take a look at the vec add function?
Oh yeah, that's the one that I just noticed it in other parts of the code, so it's already in the train function.
Yeah, this is one of my go-to helper functions when working with vectorization, because for some reason you can't address the original float 4 type with square brackets. So
yeah. So unfortunately, this can be like strictly speaking in C++, this may lead to undefined behavior, which is kind
I'm
of
not sure if
absolutely
it
stupid.
does actually in this case.
What you're supposed to use an interpret cast for is kind of maybe in this particular case it makes sense. It's going to work without undefined behavior because you
I
cast
think
to the same bit.
interpret cast is just like you interpret the bits that were there in exactly the same way, right?
Yes, but not always. Like if you like for example, if you read some data from network, and then you call your interpret cast on this to cast it to like some known type, like float or something, this is undefined behavior. What you are allowed to do is you are allowed to use the interpret cast to, for example, cast to void star, to like a void pointer, and then cast it back to some concrete type, and these two should match. If they don't, it is undefined behavior. C++ is fun.
Yeah.
Easy to shoot yourself in foot.
Oops, I still haven't configured all this. And then
I also learned today that I work at Google, and Google is very angry when people from not who work at Google and they do personal contributions to open source. You have to disclose this as working at Google, and technically Google retains copyright to the patches. So I cannot claim copyright that it is my code. It belongs to like Google.
interesting. Is that only from like a Google network, or how does that work?
Like surprisingly, like whatever you're doing, like if it's like I use personal devices, but they treat it as you're contributing to open source from Google. I guess they just want to avoid some like people start working on a personal project and this turns into a startup, and they just leave Google with and while they were working at Google, they just kind of like used the same ideas, and like proving that someone was inspired by some code at Google would be hard. So they kind of, I think they kind of just say that everything that you work on belongs to Google by default. Otherwise, you have to enroll into like a program. So that they confirm that you're not interested in this.
Interesting. Oh, oops, I added the wrong origin. Yeah, I mean, I don't even know if Amazon has a policy like that because I don't even know anyone at Amazon that's ever done anything open source, so.
So Amazon only.
in- Oh, no, go
Amazon
ahead.
only
I
have
was
used
just
the
looking
open
up.
source.
Oh, oops. I need to.
Please go ahead.
So I just looked up the dynamic, the reinterpret cast thing, and I think rule number 5 on CPP reference is what we are using here, that any object pointer type T star can be converted to another object pointer type T star 2, which is what we're doing. And then you can only dereference it safely if it's allowed by type aliasing rules, which I think, because the original struct is for floats and we are converting back to a float, should also be okay. But that's the part I'm not completely sure about.
Interesting. I'm just copying my SSH keys real quick, so I'm going to take the terminal off. Oops. For all of your workflows, like how do you commit? Do you commit directly from your host that has the the host that has
Yes.
Oh, okay. Yeah,
GPU.
I have to get all that set up. Oh, wait a second. It doesn't matter if
I created like created an SSH key and added it to GitHub and cloned the repo through with SSH.
I'm just realizing now that it doesn't even matter if I show my public key. Like,
Yeah, public key.
yeah.
The only thing they can do is allow you access to their servers.
Oh shoot! I need to two-factor authentication real quick. I'll be right back.
What I'd like to do next is I'd like to figure out what to do with NCCL to do multi-GPU support, and then use this as kind of an excuse to turn this into a video on how does it work when you have multiple GPUs on your system and you want to train the model on multiple GPUs.
Yeah, I have no experience with NCCL, so the list of things that I want to kind of figure out is quite long, and I think it's probably not at the top there, but some example code to just look at is probably nice once you've set that up.
Like the only thing that I got from this is like there is a single API call like that's called NCCL all reduce, and this implements the all reduce algorithm under the hood. But I haven't looked into the details of how this algorithm is implemented. So in a way, I'm not sure if it would be interesting at all, because what we are doing is like calling NCCL.
Yeah, but I guess that's kind of similar with all the matrix multiplications, which just go into tubulars, right? Like there you also can't really see anything interesting in the code.
Yeah, but I guess also like explaining what all reduce is. Do you know what all reduce is?
I have a vague idea.
Okay. So like, so this is probably like a good excuse to talk about what all reduce is, and how it's like structurally done, and how to add this into the code base of how to use this.
I think we're good. All right, all set. Was there anything else that people wanted to go through, or like pair programming?
Me, no. Not really.
I mean, I was just kind of joining to see what's going on here because I got a bit frustrated with my own trying to make the matrix multiplication nice, and realized that in these like subscripts where we do the like in the dev Cuda folders, we are benchmarking against like pure FP32 QBLAS, but then once you actually put it into the main file, you have to compete with Tensor Core enabled QBLAS. So even though my kernel was faster in the dev stuff, it was slower than in the actual actual run.
I wonder.
Have you been trying to use Kutlas for this? I don't remember.
No, it's actually like purely handwritten with the assumption that every shape is nice, so the kernel actually doesn't explode because they have all the corner cases to check. So it's like, it's not like something like 4, but it's like the sequence length should be a multiple of 128, I think, is the assumption. Because then you can just have like very nice blocks that do large each thread. I think it's pretty similar to what Cutlass does. And in fact, to develop this, what I did is actually I started out and wasn't really successful getting it to work from scratch. So I opened the profiler and just looked at what kind of shapes, like how many threads and how much shared memory and all that stuff is Cutlass using, and then just try to figure out like, okay, if I want to mimic that, more or less how should I organize things, and then the kernel actually developed quite nicely. So yeah.
Okay.
Yeah, well,
and basically the underlying idea was that for the attention part, we have this causal attention, right? So you actually only need to calculate half of the matrix, but QBLAS is calculating the entire thing. So even if you can't get it quite as efficient as QBLAS, as long as you're within a factor of 2, you actually get a speed up. So that was kind of my goal. And the second thing is that I don't know how much you've looked into the attention kernels that we currently have in the repo, but essentially they're an entire sequence of like you have the original matrix multiplication that generates keys, values, and queries. But then there's a permute operation that shifts things around because that makes it possible to use the batch matrix multiplication from QBLAS in the next step. Then there's the softmax, then there's the next batch matrix multiplication, and then there's this unpermute operation again. And if you have the custom matrix multiplications, you could get rid of the permute or unpermute. And within just the attention thing, like if you compare against pure QBLAS without tensor cores, it actually is significantly faster. But tensor cores change the picture quite drastically.
But you can still use tensor cores in kernels, right?
Yes, but I first have to figure out exactly how that works. Like I have never actually implemented it, but it's on my to-do list. Like a good excuse to actually learn how to do that. But yeah.
I was just checking out. We're getting like a full like pretty much 5 millisecond improvement over PyTorch right now. I wonder what it was right before the State of the Union.
That's pretty nice.
Oh, and actually, we have one more change to implement. I was copied over from the other.
So, can you talk about this once again? What is the current PyTorch speed and?
Oh, so I had to double check it because I just ran it and then it ran faster than I thought it would. But I do remember back in one of the channel conversations, someone asked that same question, saying, "Hey, like I'm running it and it's running like 20 milliseconds," and then Andre was like, "Oh, you need to run it with like these specific parameters," and so then I just ran it with those parameters, and it came out with the 70 milliseconds.
Mm.
Yeah, I think it uses like a smaller sequence length by default for generating the test thing, which is just 64 sequence length.
Yep.
Okay, and can we and so it is 70 milliseconds on PyTorch, and how much is this in the current code?
Oh yeah, it is. Oops, I just had it somewhere.
But this is full precision, right?
But yeah,
Yeah.
PyTorch is full precision as well, right?
Well, it's not actually full precision. It's FP32 with TensorFloat
Yeah.
matrix multiplications, right? Like
Yeah,
inside
and
Q+.
it's the same, right? With us, we also use TensorFloat.
Yeah. That's the same. So
Yeah, so I guess we definitely are faster. Yeah. Right.
So how much is 75? 75 divided by 70, right?
Yep.
So it's 88% faster at the moment.
And then if you remember that 80% of the time or so is actually spent in Q+, or 75%, these 8% have to come from all the other stuff, right? So all that other stuff is really much more efficient.
Oh yeah.
Yep.
I think I have one more optimization to add from Adam. This is just from yesterday, working with was when we learned how to do this in the first place.
Yeah, I don't know. Personally, I really dislike the divide there, even though it maybe doesn't make any difference in terms of.
Oh yeah, I spent so long.
Oh, wait, I think you already fixed that then.
Yeah. I realized that like you can do some just like rearranging the algebra of it and just pass in two parameters where the beta corrections is already applied to the learning rate and the weight decay, and then you don't even need to pass in the beta 1 correction. And it looks like.
So that's even nicer than I thought it would be. Yeah, that's great.
Yeah, it looks like this, but yeah, it's not the most beautiful, but
yeah, that's usually the problem. If the kernels get faster, they end up less nice looking.
Yeah. And this repository from like it is a nice learning opportunity for you to see how things work under the hood. Turns into I cannot read this code because it is unreadable. It's so much optimized.
Yeah, that's why I really like that we have the version 1, version 2, like.
Yeah. But I'm also really happy that I started looking at the repository like a week and a half ago when it was still really readable. Because now if you see it for the first time, I think you're just overwhelmed by all the stuff that's there.
Yeah, I looked at this today, and like one of the things was in the training script. I found that like there is some. Let me find what I was very confused about. Yeah, okay, found it. So backward. Okay, yeah, I looked at like the first backward layer, and I was trying to figure out like where do the weights come from? Where does the like the first gradient, where does the loss is coming from? And I found that like I found this interesting piece of code. I don't know if I can. Is there a chat in this group?
There should be one.
Yeah, I
don't
think
remember.
there's. But no, that's that's just a general thing. Like it's not for this specific. It's just a general chat.
Yeah. This is, I think, this is the general chat. In inference mode, this buffer stores the logits and logits. In training mode, this buffer will contain the gradients of the logits.
Yes, I made that change. Sorry.
So, like, you look at this and like, you think, why does this happen?
Because it's a gigantic buffer. Like it's I think like 800 megabytes or something.
Yes.
So I originally had one version where you had a union of two float pointers, one called logits and one called d-logits, and then the code would access the correct like union element. But in the end, I think, and I didn't want to have like unions there, like because that introduces another syntax element.
So
comments to this.
I get this got me very confusing. This got me very confused. And I'm sure there are many things like this.
Yeah. So I optimized the memory consumption of the forward backward paths, and that actually led to like lots of these things completely disappearing from the code. But that also makes it more difficult to see what's going on, because now instead of like named after layers, you just have some like 3 buffers that are used in several places, right?
Yeah, 3 buffers that are used for different purposes all over the place.
Yes. So one thing you could also do with the Atom kernel that doesn't make it faster, but I guess that you can kind of get for free, is that I think there are several papers stating that instead of clipping the gradients, what is actually helpful is to clip the update that you do in Atom, and all these kind of pointwise operations like clipping, they don't cost you anything because you're anyway waiting for memory. So that's something that could be easily implemented.
Oh,
but I'm not sure like if the intention is to exactly replicate GPT-2, including its training run, then that I guess doesn't make much sense. But
yeah, I think yeah, I think I'll look into it for sure, but maybe not right now.
Do you have a take on if you should look into like I mentioned in the chat that you set different batch sizes and you get different losses, different not only losses, but then you get different gradients from it, and this you kind of start getting a lot of like very different results. Is this something that we should fix?
I think it would be good to know exactly where it comes from, and then you can make a more informed decision whether it should be fixed or not, right? Like, my initial assumption, I guess, was that it might just be that Q plus picks a different algorithm that has different numerics, and then
Yep,
you get different
I also
results.
thought about this.
But I guess if you have this like strict option there, then it should really make everything reproducible. So yeah.
Okay, so what I would do is I verified. Well, first, it was very easy. Is I verified that the input texts, the tokens are the same. So I do indeed get the same data in. Just when I have the batch size of 2, I have two sequences. Then what we can do is kind of go layer by layer and see where this where the inconsistencies come from.
Yeah. Do we have any atomics in the forward pass?
Atomics in the forward pass.
I know we have them
Yeah,
in the backward pass.
this would make. I agree. Let's see. Atomic.
I think I might have to hop off to get some work done. I think I'm just gonna end the recording for now and go post this to the channel. Yeah, I guess I'll be hopping off now if any of you want to share the screen.
No, I think I should go to bed. So.
Oh. True. Yeah, 2 in the morning.
I'm not seeing any atomic ads in the forward pass.